So good afternoon. My name is Ian Bate from the University of York, where I'm a real-time reader in real-time systems. I'd like to talk to you today about some work that we're currently doing on time analysis and verification of multi-core real-time systems for aerospace applications. So as part of this, I'll first start off with an overview of the seminar. I'll talk about the current driving forces for industry. These are principally mixed criticality systems in order to reduce development costs, and this includes maintenance and multi-core. And the reason for multi-core is to enhance the functionality of systems without using too much extra resource in terms of time, space, etc. And for supply reasons, the fact that we may no longer be able to get multi-core. And then I'll talk about the requirements from CAS 32A. CAS 32A is a position paper by the aviation authorities that is giving guidance on how multi-core may be used within avionics systems. I'll then talk about what the work we're currently undertaking, which has three principal components, looking at the assessment of different processor issues, multi-core analysis and scheduling allocations, and then I'll talk a little bit about future directions. So in terms of the industry's driving forces, I think this is the important thing to talk about today, is mixed criticality allows low criticality tasks to execute on the same target as high criticality tasks. We know this, we've published there's been plenty of papers in this in many forums and by many institutions on this, but the real motivation is we will have low criticality tasks, we will support the meeting of deadlines and periods and other time requirements, but we want to have a good balance between safety, flexibility, and maximizing utilization. So this doesn't mean we won't meet the requirements, but it does mean the requirements may be slightly different. So for example, Rolls-Royce have a number of tasks considered high criticality, however could be disabled for short periods of time. A very good example here is recording error logs into non-volatile memory. It's a time-consuming process, an important process, but as long as those error logs are stored in the non-volatile memory and that no information is lost, we can afford not to run the jobs for a short period of time. So consider the fact that there may be buffers out to the non-volatile memory. As long as the buffers don't overflow, we don't lose any information. So if we don't run a couple of jobs, then as long as the buffers don't overflow, then all the criticality requirements are still met, but it allows us to drop those jobs and those tasks for a short period of time. It's also important to note that low criticality software may be developed to the same integrity levels using the same software processes, guidelines, code generators, etc. It simply may be that they're not verified to the same degree, so there may be less testing done on these. So it doesn't mean that the software is any more likely to fail. It's just that we maybe have less evidence that it does fail. And the principal benefits here are cost and flexibility. Multi-core, well, we already know they're widely being used in automotive systems. We also know that often they're used in a very constrained fashion. So we hear of automotive suppliers only using one of three cores on a tri-core device, etc. But there's also feeling they're inevitable for avionics systems. There's a broad spectrum of anticipated use and types of process being considered. The motivations are really the physical resources need to be able to do more compute power, all the way through to supply chains. So the types of anticipated uses are some are very much the same types of systems we've developed in the past, like digital engine controllers, but some of them may be much more advanced and really need that significant more compute powers. For example, if you've got a personal air taxi where there is either no pilot or the pilot is less well trained than a traditional pilot, then there'll need to be a greater degree of automation to help that person fly the aircraft and deal with safety events. So multi-core is actually currently seen as one of the biggest challenges to date, and it's one of the reasons why in a project called High Class, funded by Innovate UK, which is our funding organisation, quite a significant amount of money has been given to multi-core time analysis. Now, it's also worth noting there are many common myths around certification. Some of these live in industry, some of these live in academia. So, for example, some people will say static worst case execution time is needed for DALE. There is no such statement in the certification standards, and in fact, certification standards really dictate principles such as this and really mention timing at all. I did some work with someone called Patrick Graydon a few years ago where we talked about exactly what the certification standards say related to timing and how industry currently handle it. And actually, the answer is very little is stated. That doesn't mean that there isn't expectations from the certification standards. So certification standards will talk about things like understanding mitigating risks, establishing validated requirements and verifying them, but they won't prescribe how that is necessarily done, and they don't talk specifically about timing. So in software standards, currently we do not discuss likelihoods of failures. We don't talk of things like 99% of the time a task completes at a rate of Y, but skipping a job doesn't cause Z to happen. For example, the buffer overflow. But the key point is, currently there's no talk about probabilities and percentages such as that, but it's worth emphasizing that actually requirements such as the one written down on the slide and the one I've just talked about isn't actually a failure to meet the requirement, because the requirement would be met. It's just the requirement allows some sort of guarantee of jobs only being executed occasionally. Now, the real challenge here is socio-technical. The challenge is we're very used to writing requirements such as a task runs every 25 milliseconds and it meets its deadline. But we're not used to specifying tasks running occasionally and what happens if it doesn't, and saying, well, actually, is 99% enough or 99.9%? So the social technical issues there about how we express those types of requirements, how we verify those requirements, but equally what those requirements would be. So certification is important. It's very much where we come from. A lot of the work in York has been driven by it. And currently, certification authorities are providing some guidance which would be hard to literally achieve if you take the precise words that they say. So, for example, if you look at CAS 32A, which is the position paper from the aviation authorities on the use of multi-core, there's a requirement, a recommendation on resource usage. So resource usage for the applicant has identified available resources in the MCP. So this instantly tells us we can't do black box analysis, because actually we need to understand what's happening within the process and how that might behave. We need to identify the interconnects in the final configuration. So sometimes those interconnects are not well defined if we've not, say, started writing the software yet. The resources associated with those interconnects and the shared resources should be allocated, and that we verify that the demands of those resources are not exceeded, and we put in appropriate mitigation where they might be. So this means that we actually have to understand how the software uses the details of the processing platform, understand it and verify those characteristics. So it very much moves us away from black box analysis. Our usual philosophy in most of our work going back 20, 30 years at York is design for predictability and design for safety. So if you construct the system appropriately and when you think about predictability and safety at the onset, at the very start of the project, then it should allow you to give the necessary guarantees towards the end of the project. So why are multi-cores so difficult? Well, principally, they're designed for good average case performance at a low cost. They make extensive use of shared resources so that more processing can be done in a small unit. They have things like interconnect buses that allow, say, multiple cores to access the same device. They have multi-level caches, some of which may be shared between different cores. And they have a wide variety of other shared resources. For instance, a single CAN controller on the device might not be unusual. And then this means that software components running on different cores contend for those shared hardware resources. So why does this make things difficult? Well, the interference on execution times resulting from the contention can be very difficult to predict. We've done quite a lot of work in this area, and others have also, that can show adequately that it is hard to predict and it's hard to give those guarantees. We're certainly a long way away from giving the very hard guarantees we did in the early 90s and late 80s in terms of timing analysis. Equally, even if we've decided that we, say, like the Oryx tricores, that there are a number of variants within the families, and those subtle differences between the variants lead to some very potentially big differences depending on the nature of your software and how you're going to do your allocation, etc. So the choice of its platform, including the processor family, the variant, and whether you have an RTOS, what type of RTOS, whether you have 653 or non-653, whether you go bare board, etc., are really quite fundamental. Now, what we effectively have here is a chicken and egg situation, as the choices we make in terms of the platform depend on the software, but we haven't necessarily wrote our software yet or even planned it significantly. And the way we write the software very much influences the choices. So we kind of need to do both of these at the same time, but traditionally we specify the hardware early on, and then we start to write the software after it. So by that stage, we're constrained. So there's a number of things we can do to improve predictability. An obvious one is arbitration choices. So TDMA type policies is an obvious one for shared resources, say the CPU, but sometimes these lead to rigorous structures. So any form of spatial and temporal partitioning comes with various costs in terms of the optimality of the system performance and maintainability. But at the same time, it does give us predictability, and we have to get the right balance between those types of things. It might be instead of going down a strict partitioning approach, and a different approach might be, say, regulation. So monitoring and constraining the number of resources accesses a core can make without necessarily fixing this into, say, timing partitions. So the difference is we might just say a task can only make so many accesses to cache, but we don't say that we don't put that within a defined window. Other steps for improving predictability could be things like cache partition and scratch pads. Both of these are quite attractive approaches. They can be used in single core or multi-core devices, and we've seen some evidence of them being used and considered in real systems. The nice thing about this is it gives us a much more stable cache effect, so we can determine which piece of software is using which line of cache at any particular time or across all time. So this avoids things like cache thrashing, where two different cores have software running, they're both sharing the same cache line, and they thrash, knocking each other out of the cache and causing large amounts of inflation and other effects. So cache partitioning can eliminate this to some effect by saying this particular task has one part of partition, this particular task has a different part of partitioning. But that isn't without its problems. So a cautionary tale in work by Vaslin was it showed that having cache partition. So in terms of guidance on selection of hardware, it's important to gain an understanding of the platform and detailed behavior of its shared resources. It's important to understand how we might use that resources, and then it's important for each interference channel to understand and verify the configuration options, record our management of those policies across those resources, and come up with potential mitigation strategies where needed. So we need to gain this understanding of the platform. We need to choose the right configuration, and as part of this appraisal and selection process, we need to consider things like can full isolation be achieved? Unlikely in practice. Does the partial isolation bound maximum interference independent of any co-runner behavior? Is the interference constrained? And verify any slowdown in performance and absolute performance achieved. So basically, we come up with expectations of what we believe will happen and then check those characteristics. So in terms of multi-core analysis, we've presented before at RTNS an approach called forecast-based interference analysis, or FBI. So this is quite important in terms of the technique, even if the specifics of the techniques may not be to your liking. So the first stage we do is we decide on the most significant factors. So in our work, we used principal component analysis. So this meant that we looked at all the different sources of interference that could happen in a device, and then looked at how that would impact a particular piece of software in terms of the variabilities caused. So this allows us to go some way to meeting the needs of cache 32A because it shows that they're all considered. If we can then show that most of the factors are not, or shared resources are not significant, then we don't necessarily need to do more testing. We then move on to the next phase. So on some multi-core devices, for example, a P4080, we may have 135 shared resources. On Oryx, we may have 35 shared resources. This allows us to get down to more manageable numbers of, say, for a particular software under test, 4 or 8 factors that are considered further. We then go to a next stage where we do a lot more testing on those significant factors and we create a model. The important thing about this model is it allows us to predict for a particular type of contention what the likely inflation of the execution time is. This is important because with this, any type of model such as this, we can compare the predictions with the actuals, and by doing sufficient testing of the space in which the system will operate, and then by comparing the predictions with the actuals, we can make a judgment of whether we've done sufficient testing and whether our model is sufficiently good. So if we see predictions widely out compared to the actuals, then it either suggests we've not done enough testing and the model isn't mature enough, or that we maybe have to go back to the significant factors and choose different ones because we haven't got the right ones. So we've done a vast amount of work in that in previous years. But now what we're doing in York is we're doing a bit more work. So we've built a rig of 20 Raspberry Pi 3Bs because they're quite cheap and plentiful. We're using the full Rolls-Royce FADEX software, so that's the avionics software used to control the engines. And we aim to use this via a vast amount of testing to better understand the sources of interference and how we can characterize those, further develop any form of machine learning approach for multi-core, but importantly, look at developing evidence of accuracy and sufficiency of the analysis. So why we believe that our model is sufficient. That's an important result and should be independent of the type of modelling and testing strategy used. And the hope through this is we can make an argument suitable in the context of CAS 32A. And really the key to acceptance here is the systematic testing and the statistical analysis of the prediction accuracies. So the next stage of our work is to characterize the different types of interference. We're going to consider in our work 4 different types of interference. Firstly, no dependence. This is ideal but rare when using a particular shared resource has no impact on either task under analysis or other tasks within the system. The second category is direct interference. This is when using a resource takes up some bandwidth, and we consider this to be an additive effect, i.e., if a particular task is delayed by, say, 1 millisecond by another task using the resource, then simply the execution time is inflated by that amount. Then we have some indirect interference. This is when the state of a resource is altered, leading to both an additive and an additional effect. So this is called a super additive effect. So a good example of this would be something like a cache where another task uses the resources, which not only means the task under analysis is slowed down, but it also has additional time, say, reloading the cache. And then hidden interference effects. These are interference effects that are quite hard to analyze. They could potentially be unbounded. So examples here would be interference effects where the resources and the usage could become unbounded because of saturation, starvation style effects of resources, etc. So the next part of our work is to look at things like nuance, task model, and for scheduling and analysis. And what we mean here is we want to get away from the concepts such as execution time and move towards things like budgets. So each task would be given an execution time budget. It would be given a budget for how much it could use a particular shared resource like a cache or crossbar. These budgets could be both the amount and the phasing of those usages, but clearly it would be simpler if we kept it just to the amount. Using this type of task model means that we can then begin to compose a system in stages, consider things like task allocation and scheduling on the assumption that these budgets are then met. Taking this type of nuance approach not only would help the construction and maintenance of systems, but would also help in the argument of meeting things like CAS 32A, where it asks for interference in various parts of CAS 32A, asks for strict controls over resources, resource usage to be bounded, and the interference effects to be understood. So our current planned work is I've largely talked about the type of work we're going to do in the High Class project. High Class is a large project funded by Innovate UK, which involves most of the UK civil avionics authorities, and also some of the military ones are unfunded partners. One of the key drivers of this project is multi-core for avionics, and we're largely considering low numbers of predictable cores, bare metal type approaches, and there are different views on RTOSs when bare metal approaches aren't used, either 653 and non-653. So University of York isn't doing a lot of work on multi-core time analysis, but is advising on the information needed from it. So things like the sufficiency of testing and what it means to create a good model of this. So we're quite interested in the testing strategy to gain this information and also the architectural options for multi-core. However, our main area of work here is on task allocation and scheduling and multi-core based around these nuanced models and using the information that would come from multi-core analysis. Within the work of High Class, predictability is important. However, maintainability is going to be fundamental. And what we mean by this is we need a predictable system, but we really need to be able to build a system in stages and not have small changes to the system to have a disproportionate cost. As part of the work, we're going to harness certification principles. So there's the UK concept of a LARP, which is widely used worldwide. So a LARP is as low as reasonably practical. And basically what it means is identifying when improving safety further is going to have a disproportionate cost to the benefit that can be gained by improving safe certification. And then there's the French concept of Gambon, which is basically, in English, no less safe than before. And this is an often used tactic in safety critical systems, but basically it translates into moving from single core to multi-core doesn't have a negative effect on safety in the certification of systems. So in this sense, we need to have an argument that our system is just as safe if it ran on a single core as a multi-core, and that's a basis we can use in certification. So in terms of planned work, all the projects and all the work we're doing has a number of key research challenges, which I'd love to hear your input and views on these, but ostensibly it's the list below. How do we systematically test and understand sufficiency? How do we assess confidence in the analysis we've performed? What should the real requirements be? How to create a valid digital twin so that we can understand the typical behaviours of systems and quality of service. So the usual worst case response time analysis we do only gives us the worst case behaviours, which may be pessimistic. But what we need to do is understand typical behaviours. And for instance, when we go into the mixed criticality model, we need to understand how many jobs in a particular period of low criticality task may lose. And then what the argument and evidence should look like for certification. So do we use things like ALARP or Gambon? So the final part of my talk is acknowledgements. I'd just like to acknowledge the various members of the real-time systems group I've worked with at York for a number of years, Rolls-Royce for years of support, inspiration and access to real systems, Innovate UK for funding High Class and ATICS. High Class is the current project, ATICS is the previous one that concentrated on subjects such as worst case execution time assessment, and Howway for funding Project Mocha. I'd also like to thank members of WashU for stimulating discussions and space to think during my study leave. Without that, much of the work that I've been doing recently would not have been possible, and equally the time to write things like the grant proposal would not have existed. So I'd like to thank you for your attention, and I would welcome any questions. Thank you.